Hi, everybody. So today is the last episode of our ongoing series about algorithm analysis. Quick recap from our previous lecture. So in our previous lecture, we talked about the idea that we didn't have necessarily to implement a certain algorithm and then run it to have measurement and then derive a certain curve and then understand this curve. We could simply look at the code and try to count the statements in function of the input size. So for example, we talked about two examples, the one sum and the two sum. Here is the code for the two sum. And so for the two sum, we could even go further and only look at one single statement, which is the statement that really represents this algorithm the most, the if statement that does try to detect if we have pairs of items that sum to 0. And so by counting this statement and the number of times that it would be repeated, that it would be executed, we were able to essentially determine that this algorithm has an estimate running time of half of n squared minus half of n being the size of the input, which is like the collection that we're analyzing in that code. We saw that we could even simplify more with the tilde notation. So the idea here is to only keep the leading term and drop any other lower terms, because the lower terms, as n increases, they don't really matter anymore. So the tilde notation would keep only the leading term, half of n squared. And we could even simplify more by only looking at the order of growth of this function, which is essentially n squared. We drop the leading coefficient here. Then we saw that there were different order of growth, and I tried to show you graphically their behavior. So we saw that obviously constant never changes in function of the input size. Logarithmic is really good because it barely moves as the input size grows. Linear, the running time grows proportionally to the input size. And then linear arithmetic, quadratic, and exponential, the running time grows faster, a lot faster than the input size. And we saw that those different orders of growth, they had real life implications in terms of whether an algorithm will be fast or not. And so, for example, like given a typical scenario where we have to process an input size of 100,000 on a regular processor, we saw that according to the algorithm that we were using, like the kind of order of growth, we could have an algorithm that could process all of that data in less than a second. And if the algorithm is really bad or what we're trying to do like won't be possible, it could take us essentially an eternity. So let's resume on that. And today we're going to talk about this famous big O that you might have heard of before. So what is big O? Big O is a mathematical tool. It's a way to describe a certain function. So let me show you an example here. Essentially, imagine that you have a function here, I don't know, like something like that. Big O would be a way to express the way that this function is moving in function of the input size n. And even more, it would be a way to describe an upper bound. So big O would be a way of like, let me try to find another color here. Big O would be a way to like define another function that will always be above the function that we're trying to describe. And that function, the blue line, would be an upper bound. It would be always greater than the function we're trying to describe. Here's the formal definition to help you understand a little bit more. So we said that T of n being, so the red line here would be T of n. That's the function we're trying to describe a little bit better. That's the running time of a certain algorithm. And here, the blue line is essentially f of n. And we say that Tn is O of f of n if there is a coefficient c, which is greater than 0, for a certain constant n0, which is also greater than 0, such as T of n is always smaller or equal than c times f of n when n is superior or greater than this constant. What it means is that T of n here is O of f of n if we can find a constant c, which in fact like describes, is a multiplier to f of n, such as at some point here for a certain coefficient or for a certain, value n0, the blue line will essentially always be above the red line. If we can find a coefficient c to f of n, for which at a certain n0, the blue line is always above the red line, then we can consider then the blue line, f of n, is an upper bound to T of n. That's pretty much what it means. So let's take an example to make it even clearer. Let's look at that. In that example here, that would be a certain equation that we would consider to be this T of n. So let's say like we've done like last time, we've looked at a certain algorithm, we've counted all of the statements in function of n. And now we know that this algorithm that we're looking at has an estimated running time, which is like 3n squared plus 2n plus 4. And we are trying to see if this Tn, this estimated running time, is O of n squared, right? That means that we need to find if n squared plus 2n plus 4 is less than c, a certain coefficient, n squared. So I'm pretty much like just applying this formal definition here. So let's try to solve this equation. What I can do here is divide everything by n squared. If I divide here by n squared and all of that by n squared, so actually like let's divide this by n squared. Let me we divide this by n squared and we divide it by n squared. And now we simplify. That goes away, that goes away, that goes away, and here, and this thing stays like that. So overall, we're trying to find a c which is greater or equal than 3 plus 2 over n plus 4 over n squared. Here, it would be very easy to just set our constant n0 value to be equal to 1 and calculate now this expression. if we replace n here and n squared by this n0 equal 1, then we have 2 divided by 1, which is 2, and 4 divided by n squared, which is 1, so that makes us 4. So essentially it means that C must be greater than 3 plus 2 plus 4, which is 9. And it means that then this proposition is correct. Our Tn is O of n squared because we can find for a certain constant n0 equal 1, a coefficient C equals to 9 for which this holds, like for which C times n squared, not 9n squared, will always be greater or equal than our Tn for all n value greater than 1. And actually, like I traced it in the remainder of this slide here, and we can observe that. So the green line here is our Tn. That's this line, which what we had seen here. The blue line, 9x squared, is pretty much the one that we came up to, which corresponds to the equation like n squared times 9, the value that we just found. And we see that like for everything above n0 equal 1, the blue line and 9n squared will always be above the green line, which means that it's an upper bound. And overall, it means that this Tn is O of n squared, even though n squared technically would be lower. It would not be an upper bound if we just traced n squared, but it's not what big O is. Like big O implies that like a certain function is O of another function if we can find a certain coefficient that multiplies f of n, such as C times f of n is always greater than T of n. Okay. So that's for big O. Big O is not the only tool. There are two other notations that are very similar to big O, but that express different things. So big O is the upper bound, that what describes a function that will always be over another function. Now we have the exact opposite, something called big omega. It's the same idea of big O, but here we try to indicate a lower bound. So for example, like if I had a certain function such as, so Tn equals, I don't know, 3n squared, well, so plus 4n plus 2, I can't remember what it was. T of n would be omega of n. Omega of n here is a lower bound to this function. If I were to plot them on a graph, T of n would go like that because it's a quadratic curve, like equation. If I have n, which is just like linear, necessarily it would be always smaller. So that would be a lower bound because this lower bound would never be greater than the other equation. And the idea is the same. Like it also means if T of n is omega of f of n, it's the same reasoning with like finding a constant C for a certain value of n, such as T of n is always greater than this f of n. And so finally, we have uh, um, a last tool, which is called big theta, which here is a tight bound. It essentially means that like we would have a certain T of n, which describes a curve, and we can find a function f of n, such as we can find two constants, C1 and C2, that will always be like C2 times our bound will always be above the function that we're trying to describe, and C1 times the the big theta will always be lower. If that's the case, then we have a tight bound. So very quickly, a little bit more if you're interested in the math behind that. You have to remember that big O is only an upper bound. So technically, as we just saw a couple of slides ago, that is correct. Like we can find a coefficient C and a constant value n0 to demonstrate that 3n squared plus 2n plus 4 is in fact big O of n squared, because we can find a coefficient C and a value n0 that makes this function be an upper bound. But it's not the only upper bound of this function. We could also say that this function has other big O's, because big O of n cubed, big O of n to the power of code 4, or even like big O of factor n are also upper bound to that function, because there are also other functions that are always above the function that we're trying to describe. So you have to be careful that like big O can be a little confusing sometimes, especially if it's misused, because it expresses more. So that's why when we talk about big O, usually like we always try to talk about the tightest big O and not like any function that's above the one that we're trying to describe. Another thing that we have to be careful as well is the notion of equality. So we can say that big O of n is big O of n squared. Like it goes in that direction because n squared is an upper bound to n. Now the opposite is not true. Big O of n squared is not big O of n because it only goes in that direction. And so here, n is never an upper bound to n squared. So that doesn't work. So when you say equal, it's always in one direction. A good way to remove any possible confusion is to not use necessarily the sign equal, but to use the sign include. This way, the relationship is clear and it's always unidirectional. And finally, there's a good question here, like, why can't we not always use big theta? So actually, like, let me go back to this slide. If you remember, so go back to the slides on your own and try to remember what we had found for the problem one sum. When we counted all of the statements and their frequency, we ended up finding that the estimated running time T of n for this one sum problem was 4n plus 4. If you don't remember, like pause this video, go back to the slide, go back to the other video. So here, if we try to find the closest big O of n, or big O that characterize this function, we could find that it's big O of n, because we can find a coefficient c for a certain value n0, such that makes this equation an upper bound to 4n plus 4. Now we could also find the tightest big omega, the lower bound. And in fact, we could also prove that this t of n, which is 4n plus 4, is big omega of n. We can also find a coefficient c for a certain, like starting from a certain n0 input, such as we have an equation that's just n that is a lower bound. Altogether, it means that this one sum is big theta of n. Now, back to the question, and we could do the same for the two sum, for the three sum, for like all, like for many algorithms that are like fairly simple. We can find a big O and a big omega that are similar, which means that we can define the running time with a big theta and really like describe a tight bound to a certain algorithm. So back to the question here, why can't we not describe all functions on all algorithm always with a big theta? Because actually like most of the time it's going to be possible. But not always. There are also functions that depend on a certain input, and according to the input, according to the value of the input, they're going to behave differently. So let me show you a mathematical function that would do that. Imagine you have function f of n, which is n times 1 plus sine of n. This one, when you plot, you're going to keep oscillating between values that are essentially linear versus values that are 0. And so here, it means that your big O of n, or the big O, the upper bound would be O of n, and the big omega would be 0. And that's the best you can do. Like that's the tightest big O, that's the tightest big omega. And so for that function in particular, you cannot find a big theta to just express the curve with only one symbol. So that's why big theta, although you can you can try to use it as much as possible when it's applicable, but it's not always applicable. Okay, so let's drop the math a little bit and go back to some code. So it's good to understand all of those mathematical notions, big O, big omega, and big theta in terms of what they describe and how they are mathematical tools to describe functions and curves and express bounds. In practice, in computer science, we are pretty much always going to use big O unless you start doing like actual theory and you start specializing like that. But if you stay at a very standard like software developer level, big O is fine. We're not going to expect you to know anything else. However, even if you use big O, you should always try to use the big O function that is like that express the tightest upper bound. So if you have an algorithm that's big O of n squared, don't say that it's big O of n cubed, because otherwise it doesn't really describe it very well. What it means in practice is that like if you have a certain running time that you can express like that, and you see the leading term is in n squared, then the big O would be O of n squared. It's really usually as simple as that. So if we look at previous examples that we've studied in previous lectures, we see that the one sum, which has only a for loop from 0 to n, can be expressed as big O of n. The two sum, which had like two for loops, so going through the collection kind of twice, at least like with the combination of two nested for loops, that would be a complexity of big O of n squared. And finally, three sum, which has three nested for loops to go through the entire collection of numbers, will have a big O of n to the power of 3. Now you have to be careful. There are some cases where it doesn't, or at least like you have to be careful. So let's see why. Look at this first example here. As you can see, you have two for loops that are nested into one another. The first for loop has an index I between 0 and n, so that's going to run n times. And inside, we have a nested for loop that has a j index from 0 to 5. So here we're going to make 5 iterations. So the question is like, how would you describe this algorithm? Like what kind of big O would you apply? And you would be tempted maybe to say, oh, well, I see two for loops. I'm not going to think anymore. That's O of n squared. Except that you have to be careful. You have to always look at where is the n? Where is the input size? How does this code evolve in function of the input size, as a function of the input size? That's really the question that matters the most. If n is 1,000, then this for loop will run 1,000 times, and this one will run 5 times for every iteration of I. Now, if n is 1,000,000, then yes, you're going to run this first for loop 1,000,000 times, which is bigger than before. But you see that the inner loop will still only run 5 times per iteration of I. So overall, you do an iteration of this guy times 5 iteration of the inner loop. That is not n squared. That is O of essentially 5 times n, which is O of n. That's the complexity. And that is because the inner loop is not really an inner loop. It's or at least like it's an inner loop that is completely constant. It doesn't change as a function of the input size. And so it can be discarded. Let's look at another example here. So again, you see two nested for loops. The first one, same as before. We have an index I from 0 to n. So this one is gonna, the number of iterations will grow proportionally to the input size. And you see that we have another for loop inside j, which also goes from 0 to n. So here you could be tempted like, oh, I see a for loop that goes to n, and inside another for loop that goes to n. So this one would be n squared. I recognize a certain pattern. Except that once again, you have to be careful because this if statement here makes all the difference. This if statement will only will only succeed one time at the very last iteration, when the value of I is equal to a very specific value. So in fact, this for loop will not be executed for every iteration of I. It's only going to be executed once. So technically what you're doing is that you're executing the first for loop n times, and once you're going to execute the second for loop. So it's not a multiplication. It's an addition. It's a sum. And so here total, your algorithm is big O of 2n, which can be simplified to big O of n again, because the inner loop is only executed once. So you have to be careful about those pitfalls when you actually look at a certain code and you try to determine what is the big O complexity of that code. Okay, let's continue. So what about when you have a certain function for which you're trying to determine the complexity, so like the big O that would characterize this function, and this function calls another function internally. So look at here, we have this function which receives a certain count, and essentially we're trying to sum the different square values of that count, or at least like from all of the values between 0 up to that count. So we receive a certain count, which is the maximum value, and we run all of the values from 0 to that maximum value. We square them and we add them to a certain sum, and we return that sum. So we return the sum of all of the square values between 0 and count. Here we can pretty quickly determine we have one for loop which goes from 0 to a certain input which we get here. So that's typically O of n. Now, inside of this function, we call the square root function. And here it's actually pretty important that we know how this square function behaves. Because if this square function is also O of n, then it would multiply and we get like O of n squared. If the square function is a constant function, like if it computes the square value regardless of the input size, then it would be constant, and overall this entire function would stay O of n. So that requires you, when you write code, to know what kind of function you're calling and to know their internal complexity in terms of running time. So in practice, the square root function can be either directly a processor instruction that the processor in hardware knows how to execute, and it can be done as fast as one processor cycle or a few processor cycles. If the processor doesn't know how to do square root directly in hardware, most likely it would be emulated in software by running code that emulates the square root operation. And usually it would also take a few iterations. What's important is that the square root process, like no matter whether it's the processor that runs it or a certain software function, it always converges within a certain amount of iterations that does not depend on the input. Like computing the square root of I being like 2 or of I being like 1,500,000, like whatever number, would take pretty much the same amount of time for the processor. So overall, the square root function would be considered a constant in terms of complexity. And so this entire function would be O of n, because this for loop would be the primary would be primarily responsible for the entire complexity of this function. Let's look at another function now. another function that operates on strings. So this one is a function that receives a certain string, receives another string that is a pattern, and essentially tries to see if that pattern is included in the string. If it is included, then the function will return Boolean value true, otherwise it will return false. There are surely better algorithms than this one. This one is extremely naive, but in this one, so imagine that str is a certain string. I'm not gonna write it, but like let's imagine it's plenty of characters. And let's imagine that pattern is also a string, like that's just a small word. And so we're trying to see if that word appears anywhere in the string. With this algorithm, what we're gonna do is that we're gonna start from the very first character of the string. And we're so imagining that like let's say that the pattern is blue. We're gonna try to see if the pattern appears over here. If it doesn't, then we move to the next character and we try to see if now the pattern appears starting from the second character. If it doesn't, then we move to the third character and we try to see if the pattern appears on the third character, and so on. And so we essentially try to match the string like character by character by having we're trying to match the pattern like successively. And that's pretty much what this for loop does. We start from the very first character in the string and we compare from this character in the string with the pattern, and we compare the length of the pattern. And if we find that it's a perfect match, then we return true. If we've tried to match the pattern everywhere and we haven't found anywhere where it matched perfectly, then we would this if would never succeed, and eventually we'd be out of the for loop because we've like scanned the entire string and we'd return false. So once again here, we have one for loop which essentially iterates from I equals 0 up until the length of the string. So that's a typical scenario where we have O of n, like because we have this iteration that goes through the entire length of the string once, except that now here we call this function strnCompare. And so we need to know what this strnCompare does. And what it does is that like it will also try to go through the entire pattern, because that's what we're giving as a parameter. And it will try to see if every character of the pattern matches whatever is given here as an argument. And we see that like the function will try to match the entire length of the pattern. So technically, that's also something that's in O of n. You have to see that this n here relates to the size of the string str, whereas this n here would relate to the size, or here, the size of the pattern, which can be obviously of very different size. But we have to think in terms of like worst case scenario. It's very possible that the pattern is as long as the string or something like that. So that's why, as a matter of like simplicity, we would just say, oh, it's O of n because it scanned through an entire string. And here it's also O of n because it scanned through an entire string. And so here, because we're running this thing n times, and inside each iteration, we're also running another function that is O of n, that ends up being a multiplication, which overall means that this function as a whole is O of n squared. Okay. Another interesting case is the binary search. So let me show you the algorithm. So here, the binary search, imagine we have an array, which is a vector containing integer, and we're trying to find a certain value inside of this array. So the idea is that like we have an array here that contains a bunch of integer. We obviously assume, because otherwise binary search would not work, the array is in like is sorted, is in sorted order. Otherwise binary search cannot work at all. And so the idea of this algorithm is that like we define that the first item is at index low and the last item is at index high. And so the first thing that we do is that we compute the middle item. So we essentially add low to high, we divide by 2, and that gives us a middle item here. And we look at this item. If that's the item that we were looking for, then that's great, and we can essentially just return it. If it's not, then it means that the item we are looking for is either smaller than this middle one or higher than this middle one, or like greater than this middle one. So let's assume that the key that we would, or the item that we're looking for is smaller than the middle one. Then it means that we can simply discard all of that part of the array because we know it's in sorted order. So if this one is greater than the one we're trying to look for, then everything else is also greater and we don't need to look at it anymore. And so this guy here would become the new high. And we do it again, we do the binary search again on the remaining half. So once again, we'd go for the middle item, we'd look, is that the one or not? And maybe, no, this one is smaller than what we're trying to look for. So that would discard all of that half. And now mid would become the new low. And we would go find the middle item in between here. And so every iteration, we're reducing the amount of item that we're looking into by 2. And so overall, it means that this complexity is log of n. And the reason is that like we start from n being the number of items we have in the array. X is the number of iterations that worst case scenario we have to do in order to find the key that we're looking for. And so it means that n will be divided by 2 repetitively, like x times, up until worst case scenario, we've like really reduced the array so much that we only have one singular option at the very end. And so if we solve this, we find that x, the number of iterations that we need in order to solve this problem, is equal to log 2 of n, which makes this binary search algorithm overall be O of log n. As an aside information, for the first program assignment, you have to write a binary search function. You are very, very welcome to use this one from the slide and adapt it to your needs. As previously mentioned, you see that there is a file name here, which means that you can even find the related code directly on Canvas. And FYI, for this first assignment, I'm obviously asking you to write this function from scratch. But later in life, if you are in a situation where you want to write a C++ program and you want to use binary search, just know that it does already exist as a standard function. So if you have an array that's already sorted and you try to find a certain key in it, you can call directly binary search, which is part of directly of the standard library. Okay, and so last topic of this episode, let's talk a little bit about space complexity. Like so far, we've only talked about running time complexity, like how much time will a certain algorithm take to process an input size of n elements. Let's talk about space complexity. How much memory do we need, or does an algorithm need in order to process an input size of n items? There are two different type of memory space that we have to take into account. We have the input space. That's essentially like the space that is taken by the input data to the algorithm. And then we have something called the auxiliary space, which is the amount of new data or additional data that the algorithm has to create or may have to create in order to process this input data. Overall, what we want to do is a little bit like before, but instead of counting statements, we want to count the amount of memory that is created. So all of the variables and their size and all of that, and then try to come up with the number that is a function of the input size n. Just as a reminder, because we work here in C++, you have to remember that variables in C++, like they are declared with types, not like Python, for example. And each of those types have different sizes. So for example, like a simple character, that's always 1 byte. Short int or int, short int is 2 bytes. Usually ints are often 4 bytes and so on. So that also means that when you run, code an algorithm, you have to be careful of the data type that you choose for your variable. If, for example, like you write all of your programs only using doubles, even when you don't have to, well, you're gonna use a lot of data because doubles are pretty big. And so your program is gonna take a lot of space. So it's always something that you have to take a little bit into account, like don't declare variables of an absurd amount of space if you don't really need that space. So yeah. Okay, so let's take two examples to like kind of illustrate this space complexity. Two very simple examples. In the first example, we have a function called count letter that receives a string, receives a certain letter, and essentially goes through the string entirely and counts the number of time we find the letter that is given as a parameter. Very quickly here, you see some like cool stuff about like that were brought by C11, C++ 11, sorry. So when you have a string, for example, here, and you want to go through every character of the string, you can very simply use this form of iteration here with auto C. So that declares an iterator C that goes through all of the characters of a certain string. And so you see here that the syntax is super easy to write, much easier than like the regular C syntax. And also you'll notice that because this function doesn't modify any of the parameters, like we get a certain string as a parameter, we get a certain letter, but inside of the function, we're not touching those parameters at all because we're just reading them as input, like in read only, we can declare them as const. And that essentially like asks the compiler to say, hey, we're expecting to use those arguments only reading from them and not modifying them. So if ever by mistake we modify them in a way that we're not intending to, you should raise some sort of error. So it's kind of a like contract for us not to mess with str or letter and keep them like this. Anyway, so let's look at two things. Let's look at the input space. What do we receive as a function of the input size? And so here it's pretty much like the string. So if the string has 5 characters, then the space that will be taken will be 5 bytes. If the string has 10,000 characters, then the space will be 10,000 bytes, and so on. So here the input space complexity would be O of n. And inside, we're only declaring 2 variables. We're declaring a count, that's a single variable, and we're here declaring a C to go through the string, that's also a single variable. So that's completely constant. So overall, we would say that the memory complexity for this entire function is just O of n, because we have the input size being O of n, the auxiliary space that is created by the algorithm is always constant. It doesn't depend on the input size. So overall, that's what we have. Let's look at another function now. So this one is called string uppercase. The idea is very simple. We receive a certain string, we copy it into a kind of temporary string, then we go through all of the characters of this output string, and we modify all of the characters to switch them to uppercase. So very quick mentions here of cool C++ stuff. So here, once again, you see like the syntax, the C++11 syntax using auto. You see a little difference here between what I had done in the previous function and what I'm doing in that function. You see that here I'm using the ampersand sign, which means that I'm getting a reference on each character. And it's actually very important that I do that in that function, because I really want to change all of the characters of this input string. And if I want to be able to change those characters, when I iterate through the characters, I need to get references from them. In that case here, if I were to have my iterator C go through the string, if I wanted to change the value of C, because C is only a copy of the character that we're iterating through, it wouldn't have any effect on the input string. Here, because we are have a reference, we're actually going to change this output. So that's one thing. The other thing that I want to mention is that this function toUpper necessarily expects an unsigned char as an input. Otherwise, the documentation tells us that the behavior of the function might be undefined, which is a bad thing. Because this C character here, we declare as auto, we are delegating the responsibility to choose what type should be chosen. We tell the compiler, like we ask the compiler to do that for us, just like, yeah, auto, like pick whatever is fine. We actually have no guarantee of what the compiler will decide to choose. All that we know is that it will be the appropriate data type in order to go through each character of the output, which is great. But we don't know if this auto will necessarily be unsigned char. which is what the two upper function expects. So that forces us just to make sure that like we're square. We need to cast whatever C is into unsigned child, just to make sure that like these two upper functions will receive a character of the proper type that it knows how to deal with. So that's it. Anyway, back to memory complexity. So we see that this input will obviously have a complexity of O of n, has a number n of characters. And we see that because we make a copy of this input into an output, we also create some extra space of n characters. So total, it means that we have O of n here plus another O of n there. So total that we create, and then we have this reference C, which is like just a space of one, so it's constant, we don't really care. But so that would be 2 O of n, which ends up being O of n total. So that concludes our topic about algorithm analysis. The next homework, the written homework that will published at the end of the week and that you will have to work on next week, will be about this topic of algorithm analysis. And starting next lecture, we're going to start talking about actual data structures, and we're going to start with lists. So stay tuned.